Hi everyone, we'll be starting in about 1 to 2 minutes time. Alright, good evening everyone, and today's lecture is basically going to be on block diagram representation and how do we actually move from our mathematical differential equations into a visual block diagram itself, as well as how can we use the block diagrams to resolve our system transfer function by literally following the flow of the signals throughout the entire block diagram to obtain this transfer function equation. So the question is, why are we going to be doing this in particular? So in our engineering designs, we tend to start with some real world problem. And afterwards, once we have this real world problem, before we actually do anything or spend any money behind it, we model it in some sort of simulation or of such to reduce cost and for us to reduce any potential damages that actually can occur. And in doing so, once we have this simulation model in some form or fashion, we then test it in that simulation software itself. And if it doesn't work, we keep on improving the model or refine it and retest it until we actually do get it to work. And once we have a working model itself, giving us our actual representation, we then figure out how we can actually model this into real world components. Oh, the audio has issues? Okay, hold on. Let's see if I can actually resolve this. Is this any better? Is everyone hearing me properly? Yeah, I just realized that I had two sources on my setup, so the audio probably may have been coming in a little bit weird. So, yeah, it's supposed to be better now because of how I had the audio set up. Yeah, okay, so yeah, alright, so I'll restart because I pretty much figured out that no one heard what I said from the start of the lecture. So let's go back one slide. Alright. Okay, so today's lecture is going to be focusing on how do we represent our mathematical differential equations into visual block diagrams themselves, as well as how do we manipulate these block diagrams or resolve these block diagrams back into a transfer function equation in particular. And how we're going to do this and what you'll observe in today's lecture is that we actually follow the flow of the signals throughout the block diagram to obtain our transfer function equation as of such. So the reason why we're doing this in particular is that when we actually encounter an actual problem in the real world, we can't just go and rush off and just buy components and not analyze any sort of risk factors and such. So typically we try to simulate or model this real world problem. And in simulating and model it, we reduce cost factor as of such, and we also mitigate risk factors as well. And once we have a simulation model, we then test it in the simulation software, and then we see if it actually works to produce the desired outcome. If it doesn't work, we go back to the model and we keep on refining the model and retesting it until we actually obtain a working model. And once we actually have this working model, we then implement it using real-world components to actually achieve our final solution. Now, in modeling it, so far what we have seen throughout the entire course is that modeling any real-world problem tends to rely on some sort of differential or integral equations as such, but typically we use the differential forms. And once we have those differential forms, we then transfer those into the S domain as we saw, using the Laplace transform in order to test our model accordingly. And once it works, we then transfer it back into the time domain and implement it using real-world components. And this entire blue shaded area here for the modeling, testing, and if it works and whatnot, it basically relies on a lot of mathematics that we have seen so far, but also relies on simulation software that actually can do the mathematics for you, so a lot of computational stuff as well. So, in modeling our physical systems, as you have seen here, in particular is that we tend to watch these from a circuit standpoint because we're only focusing on electrical circuits. And then from our electronics knowledge that we've saw so far is that it's possible to represent this using some sort of mathematical equation. Because this being our op-amp integrator equation. And then we're able to transfer this into the Laplace domain as such in order to do our analysis. And then once we finish our analysis in the Laplace domain, we just do the inverse Laplace to get back the actual answer as of such in order to simulate or model our actual components for the response that we require. So if we analyze our first order general differential equation here, which is dy dt plus ay of t equal to b1 dx dt plus b0 x of t, and let's say we make dy dt the subject of the formula, so we just carry across the ay of t here onto the right hand side of the equation, and then we integrate both sides with respect to t. This dy dt here will become y of t, dx dt will become x of t, all constants remain the same, so b1, b0 will remain the same as such. But because this is b0 x of t minus a y of t, this entire thing needs to integrate with respect to dt as of such. So we will be focusing on the integral equation here that we just obtained from integrating our general first order differential equation. And we want to actually figure out, okay, how do we actually draw a block diagram representing all of these components here in this mathematical equation? So the first thing that we do is that our x of t signal is what we refer to as an input signal. We put those onto the left hand side of the paper that we're going to be drawing on. And our y of t signal, which is going to be the output, we put that towards the right hand side of the paper which we're going to be drawing on. We then see that coming out to the output here, we're going to have an addition which is mapped here accordingly between two major components. These two major components being the b1 x of t signal here and the integral equation here as of such. So we draw a summation towards our y of t here because this summation basically gives us our final answer between the two major components. We then watch our feedback here accordingly from our output. So we have our y of t signal here inside our integral, but it's going to be minus a y of t. So that means because it's going back into our system here, that means how it's minus a y of t. We draw a line from the output y of t here, connecting to our a component, so this will become a y of t, and then we then submit this accordingly here to our negative sign, saying, okay, we add this accordingly with our b0 signal here, which is b0 x of t. So basically, b0 x of t here is represented from our input, because x of t is our input. So the b0 component here being multiplied by x of t. So this is going into a summation junction, and these circles are what we refer to as summation junctions in general. And then we need to factor in our minus a y of t signal here. So we have y of t on the output here. We feed that back in to a component, so we get a y of t here. And then because this is minus here at the summation junction, this point here needs to be negative in order to compensate for what's in this equation here. We're going to move on to the integral sign in a little bit, but we just realized that this entire depiction here was just for this equation here in the bracket so far. Our next step will be to factor in our integral part here. So this will be actually at the output of the summation junction, which represents b0 x of t minus a y of t. And then this undergoes our integral equation as of such. The output of this integral will go towards the summation junction that we did at the start of mapping our block diagram. The only other component that we need to map now is b1 x of t. And as of such, we just draw from the x of t input signal here, leaning towards our b1 multiplicative component, and then we add this accordingly to the result of the integral of b0 x of t minus a y of t. And this actually completes our block diagram. So are there any questions in particular as to how this block diagram was resolved, or do I need to go back through any particular steps as well to explain anything that was a bit unclear? Alright, so okay, I'll go back through it in particular, step by step. Alright, so in drawing the block diagram when we start off here, our inputs are represented on the left hand side of our diagram, and our outputs are represented on the right hand side of the diagram. So anything that's x of t will be on the left, and everything that is y of t, being our outputs here, will be on the right. So basically, x of t signals are inputs, y of t signals are outputs. And inputs are on the left, outputs are on the right. What we're going to be focusing on here, in particular, is this part in the brackets, which is b naught x of t minus a y of t. Now remember, this entire signal here needs to map back to y of t at the end. Be in the equation here, b1 x of t plus the integral of this in the brackets here. So we want to focus on only the components in the brackets as our first step here. So we know that this b1 x of t being our first component here, and the integral part here, with the brackets being our second component here, is connected by this plus sign here. So we basically draw a summation point here, or summation junction here, to map the addition of this b1 x of t signal and the output of the integral part here as of such. So this is the reason for this summation point here. We then move on to mapping the equation inside the integral here in particular. So let's watch for the b naught x of t part so far. So the b naught x of t is just basically connecting the x of t signal here to a multiplicative component b naught. And the sign in front of this is positive, so we connect this as a summation junction saying, okay, this is positive here as of such. The minus a y of t signal is coming from the output because the output is y of t. So this goes back into our system because remember, we need to achieve an entire y of t signal here at the end. So we draw a line from y of t here, going towards a multiplicative component a, which will give us a y of t. And as of such, this negative sign here needs to connect back to the summation joint here to give us the minus sign here. So this summation series here, basically, or the summation junction, gives us b naught x of t. And at this point here, it's minus a y of t, which will give us the equation that's inside the brackets here. The reason why it feeds back is because, remember, at the end of the day, we want to get our y of t signal. So everything on this right hand side of the equation basically can be considered, okay, all of this needs to feed back somehow to our input signals accordingly. Even though if we have an output signal here on the right side, we basically map this back into our inputs here because the output overall is going to be y of t as of such. So now that we have to consider the bracket equation here being b naught x of t minus a y of t, the next step is to factor in this integral part here. And the integral part here is going to be at the output of the summation junction, which represents this equation here in the brackets. And then we just say, okay, this undergoes a integral operation here. So we just factor that in. And then this entire integral operation here factors to this plus sign here, mapping the two major components that we started with. So this here at the output of the integral is going to be plus integral of b naught x of t minus ay of t dt. The last component that we have to factor in is this b1 x of t signal here. And this just is the x of t signal here mapping accordingly to a new b1 multiplicative component and then adding that at the output of the summation junction here. And the result would be at the output here going to be b1 x of t plus the integral of b naught x of t minus ay of t here. And that gives us our final representation for our block diagram. So, like I said, the reason why we have negative ay of t here, this is on the right hand side of the equation. And as of such, because we're trying to get an overall y of t here to be on our output, because it's minus ay of t and it's on the right hand side of the equation, this needs to feed back into our system accordingly. And the reason why it is the negative here is represented by this summation series or summation junction here in particular. Is there anything in those steps that needs a little further clarification? Alright, so hopefully you guys understood that, because I'm not seeing any questions in the chat at this point. So, in watching the components here in our block diagram, we basically can see how each one of these physical components can be mapped to different points in our actual block diagram. So this summation junction here is basically our summing amplifier. The minus ay of t part here with the a component here is actually mapping or inverting amplifiers as such. And the integral sign here is, well, blatantly obvious, this being an integrated amp as such. And all of these components here are basically real circuits. So you can basically use a block diagram in particular to actually map out your real circuits in such a simplified form. Instead of actually having to draw, say, okay, well, we have to draw a physical op amp here, physical op amp here as such, and then draw the connections using the resistor diagrams and so forth, or the resistor symbols. You can actually represent this using block diagram instead, as of such. Right. So things get a little bit tricky when you get up to the second order differential equation modeling, but in reality it tends to be a lot simpler when you watch it from a block diagram perspective. So if we start with our general form or second order differential equation here, where we have d2i, dy, y, d2x, x, dx and dx here, and x, sorry, yeah. and we make d2y the subject of the formula, meaning we transfer across our a1 dy of t and a0 y of t, and we then integrate twice. So our first integral will give us dy of t, and we get rid of all our d2y, d2x components here, and we get it down into a first order differential equation, and then we integrate again at this point to get it into y of t as of such, and we get this form of this form from our differential equation here into a full integral equation. We can then see how we can map this integral equation here using block diagrams as of such. So to answer your question, not everything in life is going to be an amplifier. Just for this particular example, I showed you guys why this is an amplifier, because gains and resistances typically tend to be multiplicative components, but when you get to things like capacitance and inductance, you'll see that the capacitance tends to be a differential, and your inductance tends to be an integral in particular. So different components will have different mathematical representations as of such. So now that we moved from our second order differential form here into our integral form here, with y of t being the subject of the formula, basically the full mapping of this is given by this block diagram here. And yes, it looks a little bit scary as of such. And oh wait, hold on. Let's see. Differentiation actually can be represented on a block diagram, but I'm showing you guys this from the integral point of view because I need to transfer this into the S domain afterwards. It's a lot easier to work with integrals when you're doing the S domain. Oh yes, so yes, thank you for that correction. There needs to be another integral form here as of such. Laser pointer. So this is to be another integral sign here for the entire thing. Yes, thank you for that correction. Such, this is to be another integral sign here as well. It's a double integral. I'll make sure to update the slides accordingly with that correction. That. Alright. So yeah, so our second order differential equation, when we mapped it into the block diagram, it looks a little bit scary. It's like, okay, we have so many different levels at this point, but let's see. Right, so if we watch this green shaded area here, doesn't this look familiar? And the reason why this looks familiar is because this green shaded area here is actually our first order differential equation block diagram. And basically, it comes like we just take the output of our first order differential equation block diagram here, and we feed this in as our input towards our second order differential equation. So, representing block diagrams for different orders, let's say we go up to the third order, it will be like the first order feed it into the second order, then going into the third order as of such. And for this particular case, this green shaded block here represents our first order block diagram, feed it in towards our second order block representation here as of such. So it's a lot easier to actually see how the components actually work with each other as of such once you have it in a block diagram form. And you don't have to be watching all these long mathematical equations to figure out how to resolve them. And yes, so far we've been watching these block diagrams with respect to time, but it's a lot simpler to watch these block diagrams when we move into the Laplace domain, which we're going to get into in a few slides. So in transforming the block diagram, let's watch it for a first order differential equation block diagram. And where we had our x of t signal as of such, and our y of t signal here with our b0, a, and b1 components with our first integral here, and our summation junctions here as of such. So all constants when you transfer from the time domain into the Laplace domain or S domain, will basically just remain the same as of such. So I have a question here. So the first order feed into another first order gives a second order equation. Yes, typically it does, because we have the second integral form here as of such. So yeah, if you just add the first order to another first order here, you basically get a second order equation. But the representation here is that the first order block diagram here acts as the input for the second order overall block diagram as of such. Right. Here. Right. So in transforming our time domain block diagram here into the Laplace domain, all our constant blocks here being B1, A, and B0 are going to be unaffected. X of t and y of t, as we saw from when we did the Laplace, transforms to x of s and y of s. But the question is, what does this integral block here transform to? And the reason why we've been doing integrals so far is that once you have an integral block here, all the integral blocks here just transfer to 1 divided by s in the Laplace domain. So it's a lot easier to work with integrals with respect to the time domain block diagrams, and when you translate it into the Laplace domain, that integral sign just automatically transfers to 1 divided by s as of such. Because we have this in the Laplace domain now, because we have everything with x of s, y of s, our constants remain the same, and our integral part here became 1 divided by s, we actually can resolve our y of s equation here into x of s. And I'll show you how we actually resolve this. So let's watch this accordingly. So we have the x of s component here going here towards b1. So this will be b1 x of s at this point here. And if we watch at this point here, and this a little bit, this basically is, we had b0 x of s, and we have this negative part to consider in particular. So this is going to be minus b y of s, and then if we consider this point here, this is going to be b1 x of s plus our b0 x of s minus a y of s is going to be equal to y of s. If we transfer all our y of s to one side, so we have y of s here is going to be multiplied oh wait, I forgot to factor in something. Right. So our equation here being b1 x of s plus b0 x of s minus a y of s. This is going to be all multiplied by 1 on s, because we have to factor in this block here as of so. Right. So, and writing out our equation here, because I know it's a little bit jumbled, we basically have our output is going to be 1 divided by s into b1 x of s plus 0 x of s minus a y of s will be equal to y of s. Let's carry across that 1 of s, basically if we multiply both sides by s. So we end up getting s y of s, And let's transfer across this minus ay of s here, plus ay of s to be equal to b1 x of s plus b0 x of s. And if we factor out our y components and our x components here, we get y of s into s plus a equal to figuring listen out a component here as such, but I'll figure it out eventually. B1 plus B0 x of s. Better. Did I figure? Ah, okay. I see what I mean by error. Okay. Apologies, but let me start over so that way you guys can see where I actually made that error. Alright. So, let's start with this part here. This is going to be b1 x of s. Alright. And then let's watch the output here as required. So, if we watch here, this is going to be b0 x of s minus e y of s. There we go. No, the entire equation is not multiplied by 1 on s. That's why I'm redoing it, so that way you guys can see it. Because I understood where I made my mistake. So that'll be the output there. The output at here is going to be b0 x of s minus a y of s all divided by s because of this 1 on s component here. And then if you obtain the outputs here, this now is going to be b1 x of s plus b0 x of s minus a y of s divided by s, and this will be equal to y of s. Now, if we take this equation here and we multiply both sides by s, so we'll get s y of s is equal to b1 s x of s plus b0 x of s minus a y of s. And then let's carry across all the y components onto the left hand side and all the x components onto the right hand side and factorize it. So we'll get y of s into s plus a, because of this a y of s component here being transferred across, is equal to x of s into b1 s plus b. At this point, you can actually see how this entire equation here transfers to that form here. So the mistake I made when I was doing this in particular was I thought the entire 1 of s here was multiplying by the entire equation as of such. But that wasn't the case, because as we saw when we were resolving the equation here at this summation junction, and the output of the summation junction here was b0 x of s minus a y of s because of this negative sign here. And then the output at this point here, after the 1 of s being our integral form, is going to be this entire equation here just divided by s. But the b1 x of s component here is not being divided by s. So that's how I end up getting the correct equation here. Then I multiply both sides by s, so that means we'll have sy of s. This b1 x of s now multiplies by s, so we get b1s x of s. And the s's cancel here for this part. So we get b0 x of s minus ay of s. And if we carry across this minus ay of s onto the left hand side, that becomes sy of s plus ay of s. And we can just factor out the y of s here, so we get s plus a. And the right hand side here is b1s plus b0 all multiplied by x of s. And you can carry across the s plus a here onto the denominator, and you can get the resultant equation here as of such. Alright, so most likely in doing those steps and seeing where I made that error and then rectifying it to show how do we correct for this error, actually give you guys an idea of how we actually can resolve block diagrams in particular. Is there anything that I need to go back through when I was resolving this block diagram that needs a little bit of more explanation? The reason why we got the sy of s in particular was because once we obtain our y of s equation here at our output, and we multiply the left and right hand sides by s, that's how we get sy of s here. And the b1 x of s that now multiplies by s, so we get b1s x of s. And this part here that was divided by s only, the s's cancel when you multiply, so you just remain with the numerator factor here. I don't think there's any further questions at this point, so I'll go on to the next slide. So when we're dealing with block diagrams in particular for any sort of engineering that represents our electrical components, or it could be any other sort of components, be it chemical, financial, and so forth, we tend to try to represent these into the Laplace domain or the S domain because it makes our work a lot easier to conduct instead of trying to do it into the time domain. And we saw this trend in particular for when we're trying to solve for differential equations in the time domain, how long the work intends to be. And it was a lot easier to solve it in the Laplace domain and then do the inverse Laplace to get our final answer. So as such, any block diagrams we're going to be dealing with from now on throughout the entire course will be done using only the Laplace domain or the S domain. Once we obtain our transfer function, we can then convert the equation back into the time domain if it's asked of you or if it's desired of you. So basically, we saw how we can resolve that first order differential equation transfer function from that block diagram. But I just need to reiterate a little bit how we go about doing like simple transfer functions as such. So in doing this simple transfer function, basically all the components here, once there's no summation junctions, they tend to multiply by each other straight throughout. So this x of s here will multiply by 1 divided by s plus 1, which is our h of s component. So that's how we get x of h multiplied by h of s here be equal to y of s. And then we can substitute in h of s here accordingly for what it represents in the block. When we have parallel interconnections, we tend to find the outputs of each one of the branches that leads towards the summation junction in order to get to the output of the summation junction as such. So we watch this summation junction here and we say, okay, this line leading to it is going to be y1 of s, and for the next line we say it's y2 of s. And then we resolve what y1 of s is going to be in terms of the input signal x of s, as well as the same for y2 of s. So we say y of s is going to be the summation of y1 of s plus y2 of s, because the summation junction here has positive signs. And then we say, okay, what's going to be y1 of s? So y1 of s here is going to be x of s multiplied by h1. So we get that here. And then for y2, we get x of s multiplied by h2 of s as of such. Now we substitute in our h1 equation and our h2 equation. We can also factorize if we want to get it to a simpler form. We get our final equation here being in terms of the output y of s and the input x of s only. And parallel interconnection typically represents how do we represent any transfer function into partial fractions, because the equation itself is just going to be a summation of individual components. So once you see individual components summed up to each other, it's basically going to be a parallel interconnection in the block diagram form. For the serial or cascade interconnection is where we tend to have blocks being represented sequentially. And basically, as we saw from the first example, which was a simple block diagram, once we have sequential block diagrams, we just basically keep on multiplying straight throughout no matter what. So this comes like, we say the output of the first h1 of s, we say this is y1 of s, and then the output here, which is y2 of s at the second block. So we say y1 is going to be x multiplied by h1, then y2 here is going to be h2 here multiplied by y1 here. And we can combine all of these in terms to get this in y and x only. And we see basically y of s is just going to be h2, h1, x of s. So the reason why y of s and x of s are in the block diagram is because y of s represents our output signal in the Laplace domain, and x of s represents our input signal in the Laplace domain. The reason why there are 1 in these block diagrams, the 1 just basically does not give any meaning whatsoever. You could actually ignore the 1s here. That's how it actually drew out when I actually did the diagrams as such. So these 1s here serve no purpose whatsoever. They just were basically placeholders at this point in time. So, right, so because we know y of s here is going to be just a multiplication of all that came before it in the serial or cascade interconnection, y of s here is just going to be h2 multiplied by h1 multiplied by x of s as of such. And then we could just substitute in h2 and h1 as of such. So, typically, the approach I showed you guys in this lecture is how do we move from the equation to the block diagram. But when the questions come, it's more of how do you move from the block diagram back into the equation. So you wouldn't get any questions giving you the equation and then, okay, say you need to draw this into the block diagram form. You will typically be given the block diagram and then asked to resolve the equation and then possibly to obtain the time domain representation of the equation afterwards as of such. In particular, when you start getting complex block diagrams, there are some techniques that you will see in the next lecture. How do we reduce those block diagrams to get it into a simpler form for you to resolve the actual final equation? But that's in tomorrow's lecture, and I'll go through it in detail, those techniques, and how we can actually apply those techniques to reduce your block diagrams and get to a final equation as of such. So the cascade or serial interconnection is what it's done when you express your transfer function in poles and zeros. So it's typically like when you have all your roots on your numerator and denominator multiplying with each other as of such. So the next example, which is example 4, is probably the most important example that you need to pay attention to, because this actually forms the basis of doing block diagram reduction. And this is what we refer to as feedback. Now, The reason why we refer to this as feedback is because the output here, y of s, goes back towards our input x of s. And once we have this connection going back towards our input, we refer to this as a feedback as of such. This particular example we refer to as negative feedback, and the reason for this being is that if you watch this line here from y of s going back towards x of s here, at the summation junction is represented by a negative sign here. And this negative sign means that the entire block diagram here is what we refer to as a negative feedback system. So we now have to figure out, okay, how do we resolve this block diagram in terms of y of s and x of s? So we use intermediary signals in order to obtain this equation as such. So we basically say, okay, we need the output of the summation junction. So let's the output of the summation junction here be equal to x1 of s. And we say, all right, so what are the inputs of the summation junction to give us our output? So we see here that there's x1 of s here, and then we have this negative feedback here coming in from y of s. So let's say the output here from the negative feedback is going to be y1 of s. So we say that's going to be x of s here minus, because we have this negative sign here, y1 of s. So okay, the next question is, what's going to be y1 of s? So y1 of s here is basically y of s here feeding back into h of s, and because of the serial connection, it's going to be a multiplication. So y1 of s here is going to map to y of s and h of s. So we knew that the output of the summation junction here, x1 of s, was x of s minus y1 of s, and we know that y1 of s was basically y of s, h of s. Now we consider our feed forward path here, because we're already taking care of our feedback path here, and we figure, okay, what's going to be y of s here in terms of just only this feed forward path here. So we consider the output of the summation junction just moving towards y of s. We have this x1 of s signal here going into our g of s signal here, and that's going to be a multiplication. So y of s here is just going to be x1 by g of s. So now that we actually have all those signals here, we can just substitute accordingly to get towards our y of s signal. So this y of s signal here will now become y of s is equal, and we have our x1 here, g of s into x of s minus y1 of s. But now we need to figure out, okay, what's going to be y1 of s. So I'm transferring this equation onto the left hand side here. So we now need to substitute in y1 of s here. So we get y of s is equal to g of s into x of s. Oops. That's minus, and now we have y of s here. So this is going to be y of s, h of s. So let's multiply this out. Y of s here equal to g multiplied by x of s. So I'm just shortcutting a little bit, which is perfectly acceptable if you guys are doing it in the exam as well. Minus g y h of s. So let's carry across all the y components onto our left hand side of the equation. So we get y of s plus g y h of s equal to g x of s. Let's factorize out our y of s here. Get that into 1 plus g h of s, g x of s, and then we just want the y of s on the left hand side of our equation, so we get y of s here equal to g x of s all divided by 1 plus g h of s. Newton. And that basically gives us our final equation as of such. So after doing all those substitutions and whatnot and so forth, we arrive to our final equation here for our negative feedback transfer function. We refer to this more generally as our closed loop negative feedback system because the sign here is negative. If the sign here was positive, we will refer to it as a closed loop positive feedback system. Now, it is helpful for you to actually memorize the equations for a negative feedback system and a positive feedback system accordingly. So the equation here is given to you for the negative feedback system. I think later on, as your homework, you're going to have to resolve this for the positive feedback system on the last slide, but we'll get to that if it's there. So all the working that we saw here on this previous slide gives us to our final transfer function equation here in terms of y and x, where y is on the left hand side and x is on the right hand side. So we get this in terms of our transfer function as of such. And you actually can memorize this and apply it accordingly. There's no need to derive this as of such when you're actually doing your block diagrams. This is actually a standard form for negative feedback, so you can just memorize this. The same thing with the positive feedback system. You can just memorize the equation and just apply it accordingly. And that's perfectly fine. So for your first homework here, because we just basically resolved our negative feedback system, you now have S-domain equations for G and H. And I want you guys to actually do the substitutions for homework and see if you can get this answer here for Y of S accordingly. And then, oh, all right, okay, yeah, right. So there's also some step response analysis that you can actually do for block diagrams, and as of such, if you remember, your step response here was basically u of t in the time domain for x of t. But when you transfer this into the Laplace domain, it's going to be 1 on s for x of s. And then once you have this in this form here, you can then multiply out accordingly. You can expand it into partial fractions. And once you have the partial fractions of such, you can obtain this back in terms of y of t, and then you can actually plot y of t accordingly to see what the response is going to look like. If the poles here, being the roots of the denominator here, are simple, being they're real and there's no imaginary components, when you do the inverse Laplace transform, you'll get dk and exponents, which will basically be exponents to a negative power. But if they're a complex in nature, you will end up getting sine and cosine terms when you do the inverse Laplace transform. So for this particular example, you're going to get two complex poles when you actually start resolving it for the step response. And it's possible for simple poles to combine to create complex ones once there's the introduction of an imaginary component for those poles as of such. So in plotting the step response, what we see here basically is that yes, we get a nice smooth rise time here as of such for step response. This system, as we saw when we did our first and second order block diagram analysis, no, first order, second order system analysis last week, it's not going to be overdamp and it's not going to be critically damp. So as of such, it's going to be underdamped slightly because we have a small little ripple here as of such. Right. So for your second homework, instead of having negative feedback here, you're now going to have positive feedback. And I want you guys to actually do the steps and try to resolve this to get the actual transfer function as of such, and then substitute in g and h to see what your resultant equation is going to be. And to give you guys the answer of what it's supposed to be, you're supposed to get y of s here is equal to g of s multiplied by x of s divided by 1 minus g of s h of s. So you're supposed to get that answer when you actually resolve this for the positive feedback system. Alright, so that brings us to the end of our block diagram representation lecture. Tomorrow's lecture is going to be focusing on how do we do block diagram reduction, especially when we have complex block diagrams and we need to obtain our final system transfer function. So we're going to be looking at particular techniques tomorrow. How do we apply those techniques to reduce block diagrams in particular, as well as the strategies employed when you're actually reducing complex block diagrams. So if there are any questions at this point in time for any of the material in this lecture, please ask them now. Alright, seems like we don't have any further questions, so if anyone has any further questions, please feel free to leave them in the comments down below or email me accordingly, and I will answer those questions and resolve any misconceptions or anything that you're unclear about. But as far as how the chat has been going here, we have gotten questions throughout the entire lecture, so there doesn't seem to be any final questions at this point in time. So remember, tomorrow's lecture is going to be on block diagram reduction, which is actually a sort of important topic, so try not to miss tomorrow's lecture. So until then, take care, be safe, and I'll see you guys soon. Later.